Okay, we just wait one more minute, maybe we can get started. Okay, let's get started then. I think I was asked to put on my earphone. Okay, I'm going to do a review session today on all the knowledge that we have learned so far in the course. And after the lecture, I will give you a take-home exam 1. And I will make it so that it is due on Monday night, midnight, so that if you happen to be working outside and if you're pressed for time, you can have until midnight on Monday to hand it in. How does that sound? Is that okay? Or you want it to be handed at noon on Monday because that is another way, but I thought giving you more time would be good, okay? Okay, let's do a review today, and I'm just going to look at some of the past lecture notes and then decide on what we can do for this session over here. And I suppose you can see my screen and you don't have any problem with that, okay? So what we have done is actually to try to cover as many topics as possible, 150 years of electromagnetics knowledge and how that knowledge has been translated to impact engineering, especially electrical engineering. Yes. Okay. Okay, I thought I hear some noise just now, but it went away. So it has been more than 150 years because it was 1865 that Maxwell completed his equations. But then even before him, there were Ampere's law and there were Faraday's law, Gauss law, and so on that were prevalent during that time. And it was mainly driven by the need for telegraphy, the need for telegraphy technology. But since then, lots of things have happened, and your cell phone and your everyday life, and whatever you see when they watch TV at home, I'm amazed how Wi-Fi has helped us do so many things at home. Like the fact that I can talk to you now and see your faces is because of broadband communications that we have in this modern world. I can see pictures, I can see pixels, I can see tons of information coming through the internet, and internet's connected by electromagnetic signals. Okay, but this 150 years of knowledge is rather dense. And in this course, I cannot teach you everything. So I'm kind of selecting important topics to teach when I teach you this knowledge. So you will find that it very much follows Nyquist sampling theorem that, let me see, we cut this off. If you have Nyquist sampling theorem, it says if you have a signal, and then you have to sample at least at 2 points per wavelength to capture the signal. Okay, that's why Nyquist said many years ago. So I would just give you samples of this knowledge throughout history and try to teach that knowledge to you in the simplest way possible. So you will find that it jumps from one packet of knowledge to another packet of knowledge, and you will feel the discontinuities in between. And essentially in signal processing, we know that if you pick up this pack of information, you pick up this packet of information, you have to do interpolation to get what is in between. So the interpolation will have to be done by you. You have to go and do background reading, but I will give you the skeleton of this knowledge. And once you have this skeleton knowledge, you can actually fill out the curve a lot more easily. So the lecture notes are very terse, not verbose. Is the nature of my lecture notes. And you can use the textbook that I have posted for free on the website to fill in the knowledge in between. It can be a lot of hard work if you really want to know the details about some of this knowledge, but if you just want to have a good survey of what this knowledge is, it's not that difficult. Okay, so we teach you big concepts. Okay, and not to meddle about the details you can fill in yourself. So that is the important thing. And of course, the course is mainly centered around, I really have difficulty doing this without a keyboard. Now just to use the mouse pad to do this without a keyboard. So let me see what they can do is actually insert a lot of this blank thing, but you still have this. This is no good. Make a copy of this. And without the keyboard, it's very difficult for me. Yeah, I have to flip this around. I'm not used to manipulating this computer without my keyboard. So I have a lot of slides now without those unnecessary things that I have to delete every time. So the two very most important theorem before we started out with Maxwell's equations are the Gauss divergence theorem and Stoke's law. Okay, with Gauss divergence theorem, I would have to write it down for you again, that if you have a divergence of something and integrated that over a volume, and that would become something like a surface integral, ds, okay, and V can be something like this, and S will be something enclosing the surface V. And then this n dot is normal to the surface, and that you have studied in your undergraduate course. And the only difference we make in this course is to show you a detailed derivation of this Gauss divergence theorem that was not usually shown to you in your undergraduate course, I think. Okay, another very important theorem that we learn is actually Stoke's law, which says that if I have the curl of a quantity. And then if I do a surface integral here means n ds. Okay, the incremental surface here actually means that. And if I were to integrate this over a surface S that is enclosed by contour C, then this would become E dot dl. The L is an incremental length on the contour, and this would be a closed contour. And so this is Gauss divergence theorem. And this is Stoke's law. I better make sure that I put the apostrophe in the right place. This apostrophe is going to be going over there. Okay, with these two very important laws, which I believe were actually discovered in the 1700s, early 1800s, we can write down Maxwell's equations in differential operator form. So the four Maxwell's equations that you will see repeatedly in this course is first Faraday's law. And then the second very important Maxwell's equations is Ampere's law. And then the third one is Gauss' law for electric flux. And then we will have Gauss' law for magnetic flux. Okay. And it turns out that you can actually derive the third and the fourth Maxwell's equations from the first two by taking the divergence of the first two equations. But that only happens in electrodynamics. And electrostatics, you cannot derive the third and the fourth Maxwell's equation from the first two, and you will have to solve all the four equations concurrently. And it's something that I emphasize to students over and over again. So for electrostatics, you have to actually solve these four equations concurrently. Since now you cannot derive the third and the fourth equations from the first two, okay, this is for statics, and this is for dynamics. Let me write dynamics here. But one thing to notice is that there are actually not enough equations for the number of unknowns that we want to solve for. Usually we assume that J and rho are known. Okay, and then in this case, E, B, H, D are unknowns. So in order to have the number of equations to solve for the four unknowns, because the first two equations only has inherently just two primary equations, since the other two are derived from the first two. So we need constitutive relationship to increase the number of equations that we can have to solve them. And for the vacuum case, it is just this very simple relationship. And if you have these two additional equations, then you will have 1, 2, 3, 4. 4 equations for 4 unknowns to solve for all the unknowns that you need. And J and rho are known, and these are usually regarded as inputs. If you want to think of this as a linear system where you put in something inside and hope to get the other things outside, then the sources are regarded as input, and then these fields are regarded as output of the system that you need to solve for, okay? So one of the most important phenomenon that we like to derive from Maxwell's equations is actually wave phenomenon. And that is the triumph of Maxwell's equation. And in order to show wave phenomenon, what we did then was to actually do a very simple case of Maxwell's equation in free space or vacuum. And then we can let E be something that is pointing in the x direction, but only to be dependent on Z. Okay, and if you make this very simple assumption about Maxwell's equations, you can actually solve Maxwell's equations in closed form. So if you have curl of E is equal to minus dV dt, and for vacuum, we can say that this is mu naught dH dt. Okay, the other important equation is, of course, Ampere's law, which is the d dt, and in vacuum, this is just epsilon naught dE dt. And then we have two equations and two unknowns, and we can eliminate one of the two equations by taking the curl of equation 1. For instance, this is equation 2. If I take the curl of equation 1, I will get curl of E is equal to minus mu naught. Assuming that mu naught is a constant, then I will have this being on my right-hand side. There's one mathematical manipulations that I have done here, which is that when I take the curl of the right-hand side, I'm assuming that I can take the derivative operator inside this partial derivative and write it in this manner. This is called commutation in mathematics. In other words, the partial t and the curl operator commute, and mathematicians will write it like this. If these two operators commute, you say that they have zero commutation. So let me not belabor that point, but it's a notation that you often see in mathematics. We can substitute equation 2, using equation 2 to substitute into the right-hand side, then we will have minus mu naught epsilon naught partial square t square E. Okay, and then this equation is simple enough, but not simple enough for us to solve it in closed form. So we need to make something simpler on the left-hand side, that we use the back of the cut formula, or the fact that the double curl operator, which is written like this more explicitly, is actually the same as the gradient of the divergence of E minus the Laplacian of E. Okay, since there is no source inside our problem, divergence of E is usually equal to charge over epsilon, and then is 0 because rho equal to 0. In this problem, we are looking for a wave solution in vacuum when we have nothing there, and the left-hand side thus simplifies, and then we are now with the fact that the left-hand side becomes Laplacian of E plus mu naught epsilon naught partial square t square. I move this to the right-hand side. I will have this being my equation. And this is called the wave equation, as many of you have known. But for the simplifying assumption that we have, that the electric field is only pointing in the x direction, but only with z variation, this equation becomes something like having only z derivatives, because I assume that my function has no x or y dependence. And then I would have mu naught epsilon naught partial square t square E, and then E will be just Ex. And I have this equation, which is called the wave equation. And wave equation can be solved in closed form. And many people have done that. I think probably the first person who did that was D'Alembert. So I will not repeat the solution here, but the fact that this equation can be written in terms of traveling wave solutions. The Ex ZT will look something like F plus, let me see what I used in my lecture notes, X plus Z minus C naught T plus F minus Z plus C naught T, where C naught here will be given by 1 over square root of mu naught epsilon naught. That is the vacuum velocity of light. Okay, and you can see that this is a right traveling wave, and this is actually a left traveling wave if you do some careful study as to how these two functions would evolve as a function of time. Okay, so any questions so far? Okay, if not, then I will move on to what I cover in lecture 4. In lecture 4, then what I did there was to use boundary conditions or introduce boundary conditions. And I like to introduce boundary conditions in a non-conventional way that is different from what you see in textbooks. And in a sense that boundary conditions are also called jump conditions. And they come about because of the differentiation that you have in Maxwell's equations. For instance, if you look at Faraday's law, which says this. And in this equation, everything on the right-hand side is finite. Okay, everything on the right-hand side is finite. So since you take a derivative of a function with respect to space on the left-hand side, the function has to be sufficiently smooth in order for this equation to be satisfied. You have to remember some notions that you have learned in electrical engineering. That is, if you have a functions of space, since I'm talking about functions of space, curl of E, if I write it out more explicitly, is curl of E of R and T. And if I take the curl, I'm operating on this function as a function of space, that if you have a function that has a kink, okay, if you differentiate it once, this function would be like two constants, okay? And if you differentiate it one more time, okay, you will get 0. But at the place where you have a step discontinuity, you will get an impulse. Okay, you just remember that differentiation of a step discontinuity gives rise to an impulse function. Differentiation of a continuous function with a kink gives rise to a step discontinuity. And since I have a quantity that is finite on the right-hand side, I don't have a function like this, which is singular. Okay, then E itself must be a continuous function of space. And if E itself is a continuous function of space, and if you write out the local coordinate system of what the curl operator is, you can actually look at the curl operator that the electric field can be tangential to the surface, and then it can be normal to the surface. You can break the electric field into tangential and normal component. And when you take the curl of this thing, okay, for instance, if I call this my X coordinate locally, and if I call this the Y coordinate locally, then the curl of E is actually partial Y ET. It's partial Y EX kind of thing. If you take a curl, you're taking a component of a field pointing in one direction, but finding its change in the other direction. And because of that, you know that this function must be a continuous function in the Y direction. Okay, this function, since it produces no singularity, it must be a continuous function in the Y direction. And hence this function must be sufficiently smooth in the y direction. And another way of saying that is that this function has a continuous tangential component in the y direction. Another way of saying that is E1t equals E2t. And to write it in a mathematically independent form, you say that n cross E1 is n cross E2. Okay. The n cross operator is a nice operator if you define n to be a normal unit vector in that direction. And whenever you cross that with any vector, it picks out its tangential component. So you can see Faraday's law gives rise to tangential E be continuous because I assume that everything on the right-hand side is smooth or finite. And then you have Ampere's law. Ampere's law can be written as such. Okay, and there is a slight caveat here in the sense that this could be a singular function. And if that is a singular function, H need not be that smooth. And this is finite. Okay, this would be singular if you have a current sheet. And if you write in terms of local coordinate system, a current that is written as a current sheet, say if I have this be my y direction, and this is my x direction locally, then I can say that this current is x hat, a current sheet thing as a function of, or maybe I just put Js, and then you can think of it as delta y in the right direction, in a normal direction. So a current sheet can be thought of something that flows in the x direction, but it's highly concentrated in the y behavior so that all the current is being focused or limited to the surface in a delta function manner. And this is a singular function. And this is how you should describe a current sheet. It has a dimension of 1 over length. And the current sheet has the dimension of amperes per meter. And this current density has a dimension of amperes per meter squared. So everything works out all right. And this current sheet, if it is present, can give rise to a singularity on the right-hand side, a delta function singularity. And in order for you to match the singularity, then H has to have a jump discontinuity. Okay, and if you go through the thinking, then you get the boundary condition that n cross H1, H2 is equal to Js, where Js is the current sheet that is residing on the interface between two medium. Like if this is medium 1, medium 2, then you have this boundary condition. And of course, you have the other laws, divergence D equal to rho. And from this, by eyeballing the thing, and if you have something that is singular on the right-hand side due to a charged sheet, then you have n dot D1 minus D2 must be the charged sheet, okay? The charge density on the surface. And then you have divergence of B equal to 0 implies that n dot B1 minus B2 equal to 0. So I like you to acquire this intuitive feeling as to where boundary conditions come from. They actually come from the derivative operators. And derivative operators, when operating on the function, can only produce singularities if that function has a jump discontinuity. And these singularities can come from current sheet or charged sheet, okay? So are there any questions regarding this? So for instance, if you want a more physical picture of this, you can think of current sheets like flowing into or flowing out of the blackboard, and you can apply Ampere's law with your right-hand rule and that kind of thing. Okay, let me see. And you will find that if the current is flowing out, then the magnetic field has to go like this. So you see that the magnetic field actually is pointing on opposite directions on both sides of the current sheet, giving rise to a jump discontinuity that you expect to see from mathematics. And then for this physically, you can think that if you have some surface charges, you know the notion that electric flux always exudes from surface charges, then the electric flux has to look something like this, because they have to exude themselves from charges. So if you look at this again, you can see that the electric flux does have a jump discontinuity at the interface. Okay, so those are the kind of physical intuition that you can get. Then we learn about Green's function technique. Okay, let me see if I insert this way, it still happens that way. I don't like the fact that it always comes with this, and then it's not easy for me to get rid of it using just a mouse. Okay, so maybe I can say copy and paste.
Professor, if you right click and go to layout, you can change it to blank slide.
I can right click and go to layout.
Let me right click one of those on the sidebar there.
Over here?
No, over yeah, one of those there. So right click, go to layout.
Layout, okay.
And click blank slide. Okay,
good. There's a shortcut. There's a shortcut to removing all these annoying things that I have. Okay, so we have learned how to solve these problems, and one of the things that we learned to solve first is to do electrostatics. And electrostatics, we need to only solve these two equations: divergence of D equal to rho, and then curl of E equal to 0, and say we let E equal to minus grad phi, so that the second equation is automatically satisfied. But we know that D is epsilon E, and then we plug this into the the first equation, we get divergence epsilon E is equal to rho. Oh, sorry, am I right? Yeah, I'm still right. And then I would have this mean divergence of epsilon grad phi equal to minus rho. Sorry, I should put a minus sign here and put a plus sign, and I would be logical. And then we would have this Poisson's equation with a minus sign there. And if the medium is homogeneous, like the vacuum case, then this Poisson's equation just becomes this equation. Okay. And then this del dot del is usually written as a Laplacian. And if you work it out, it is just equal to partial squared, partial x squared, plus partial squared, partial y squared, plus partial squared, partial z squared. Okay. And we have taught you the Green's function method of solving the Poisson's equation. That is, we know how to solve this problem when we have a point source. That if we have a point source on the right-hand side, like Q delta R over epsilon naught, and we have a point source on the right-hand side, and it can be expressed as such, but we know from Coulomb's law how the potential should look like. So using that knowledge, we infer that the Green's function, which is the solution to this equation, would give me a solution that is something 1 over 4 pi r minus r prime. Okay, we know that by comparing the solution with Coulomb's law. Hence, we know how to solve the last equation of the slide by using the principle of linear superposition. then I know how to solve the equation here by using the principle of linear superposition. We learned this in impulse response theory when we did the linear time invariant systems in electrical engineering. So I could easily write down the solution that phi of R in general would be equal to minus, well, let me see if I get this correct. Okay, 4 pi. The convolution of the Green's function, which is 1 over R minus R prime with the charge. Okay, using this convolution theorem. And then we go to solving magnetostatic problems. And then in magnetostatics, we say that the two equations that we need to solve are these two equations, divergence of B equal to 0 for magnetostatics. And then I just let B equal to curl of A. And then the second equation would be automatically satisfied. Then H would then be equal to 1 over mu naught curl of A. And then you plug that back in, you get curl of A is equal to mu naught J. Okay. And then using the identity for the double curl operator again, this is gradient of the divergence of A minus Laplacian of A equals minus mu naught J. Again, we have to get rid of this by using what we call the Coulomb's gauge. Okay, this is set to be 0 using what is known as Coulomb's gauge. What it amounts to is that the vector potential A is not unique unless you specify both its curl and its divergence. So we just have specified the curl of A to be H. That's not enough. We have to specify what its divergence should be. Then the equation simplifies to this. I think I have a plus sign here, so this should be a mu naught J. And this is actually called a vector Poissons equation. And since it's a vector Poissons equation, we can solve it using convolution as well and obtain the fact that the solution to vector Poissons equation is just mu naught over 4 pi. The convolution of the Green's function with the input. Okay, the input is just the right-hand side, and this is just just what I should have. So I know how to solve the electrostatic problem using Green's functions technique. This is called the Green's function method. Okay, and then let me move on to lecture 5. Using this equation that we have derived, we can essentially, let me see if it works this way. It doesn't work that way. So I can actually go to layout and want a blank slide, and that works. Okay, thank you for pointing that shortcut to me. So then the next thing we did was to derive Bilsavel's law. And that is just a show of tour de force mathematics derivation. And it was not very deep, but very complex. You just have to do quite a bit of vector algebra. You arrive at the fact that using Green's function technique, and if you have a piece of wire carrying a current, then the magnetic field produced by that piece of wire is given by this formula over here. Okay, this is derived using Green's function technique. I wouldn't go into the detail of this. You have done a very nice homework on this. But there's an additional thing that we have to take care of, which is that boundary conditions for a conductive surface. Okay, and from this equation and this equation, okay, you can actually arrive at the continuity equation. Take the divergence of the first equation, and then you make use of the second equation. You can show that divergence of J is minus d rho dt. Okay, this would be partial rho, partial t. And from this equation, again, boundary conditions follows from the differential operators of the equation. So if we have a medium where J equals sigma E, like you have an interface J1 equals sigma 1 E1, and then the second medium is J2 equal to sigma 2 E2. By looking at this equation, you immediately conclude that the boundary conditions has to be equal to that, because everything is finite at the interface unless you have a charge sheet. Okay, if you don't have a charge sheet, then this should be your boundary condition. And then if you plug in the fact that you have a conductive medium, then the boundary condition would translate to this. Okay, so these are the kinds of things that you should be aware of in this course. And also we say that at the metallic interface, the electric field is always normal due to the fact that there could be no electric field inside the conductor. Okay, if you have a conductor where this is not zero, and for statics, E has to be zero inside. Because if E is not zero, then the current will keep flowing until charge builds up on the surfaces to stop the current from flowing. So you can see that the electric field near a conductor surface has to always look like this. Because E is not zero outside, but because E equal to zero, tangential E has to be continuous by Faraday's law. E has to look like that outside. Okay, but normal E does not have to be zero because you can have surface charges built up on the surface. Okay, so this is the behavior of the electric field inside a conductor. And using this kind of physics, you can build the Faraday cage. Faraday cage is essentially something where you mesh up with the chicken coop wire, for instance. It doesn't have to be very densely meshed, but just enough so that electromagnetic signal with very long wavelengths cannot get through. And if you ground this cage, if you ground this cage, then you set phi to be at zero potential on the surface of this cage, and the charge would flow themselves around until the potential becomes zero inside the cage as well. And then because phi is equal to zero inside, E has to be zero inside as well. And you have no field inside. Since I'm running out of time, let me see if there are important topics that we should go over. And then another concept that we should go over or remember is Phasor technique. Phasor technique is essentially Pullman's Fourier transform. That if I have a sinusoidal signal as a function of time, then if this sinusoidal signal can be written as such, then a concise way of writing this signal is actually V of x e to the j alpha, I guess j alpha e to the j omega t. So if you write this sinusoidal signal in this fashion, what you need to remember is that this sinusoidal signal can be represented by this complex number over here. And that is called the phasor. And once you are able to write a sinusoidal signal in this fashion, then there is a very simple rule of thumb, which means that any derivative will just become something like that. So if you take the phasor representation of this thing, and if you go to the phasor wall, any time derivative becomes replaced by just j omega. And it's a very powerful technique. It's a technique so powerful that you don't have to learn Fourier transform to make use of many nice advantages of Fourier transform technique. Then we introduced the concept of complex power. Complex power because any sinusoidal signal can be represented by a complex number. So if I have a sinusoidal signal V of t, a sinusoidal signal I of t, in the phasor world, they can be represented by a complex number V and then a complex number I. And then you can show that there's a complex power, which is defined by V times I till the conjugate. And this relationship has a very nice relationship with the complex power, has a very nice relationship with the time average power. That is, if this is sinusoidal, this is sinusoidal. If you multiply them together, it will not be a constant function of time, but if you take this time average, you can show that this identity is true. Okay, you can show this for circuit theory quite easily. And of course, you can generalize this to electromagnetic theory, which says that if I have instantaneous Poynting vector, which can be written as the cross product of two vectors, okay, which has the dimensions of watts per meter square, okay? And if I find a phasor representation for this, okay, and then I find another phasor representation for this sinusoidal signal, then I can show that the time average power of this time varying signal is equal to half the real part of this quantity. Okay, the proof is very similar to the proof for circuit theory, so I won't go into the detail. And then we use this to define complex power. And then you find that the complex power, which is actually very different from the instantaneous power, okay, which is given by this quantity here, has a real part and an imaginary part. The imaginary part of S is called the reactive power, and it is proportional to the time that the energy is stored in the electromagnetic field in the system. And if you take the real part of this quantity, okay, this corresponds to time average power, okay? So these are the key things that you have to remember about complex power and so on, okay? And let me see, 6, 7, 8. And then we went to look at unconductive media. That I think I would not go over because then we went and studied the Drude-Lorentz Sommerfeld model. And then we went ahead and studied the gyrotropic media. Okay, and come up with complex Poynting theorem as well. But since I'm running out of time, is there any present topic that you like me to talk to you about before we depart for today. Yes, anybody? Okay, if there are no more topic, and then we studied Faraday rotation, for instance, gyrotropic media, you should all revise that. Okay, because there will be a take-home exam problem on gyrotropic medium. We also think that gyrotropic medium gives rise to Faraday rotation. And you will have an exam problem where you can learn about Faraday rotation by just doing the exam problem. Okay. So this, I guess you have to review on yourself or by yourself. And I will not review them with you. Okay, I guess I should let you go now because it's 11:21, unless you have any pressing questions that you'd like to ask me. Anybody? No pressing questions? Then I let you go and I'll give you the take-home exam this afternoon. Okay, it should not be difficult if you have been studying the lecture notes and doing the homework. Okay, I'll let you go. Okay, bye-bye.
Thank you.
Okay, bye-bye.